We're going to tackle the limbic system. As you can see, I have many parts in many different planes, and it's a complicated system, and it has a lot of structures, a lot of connections, and a lot of new names. So maybe we should start with a computer-generated graphic made from reconstruction of real brain sections. Let's look at one of those. This 3D animation is in low resolution because it's so old, but it's better than any other animation I've found to try to understand the limbic lobe, which consists of the green cingulate gyrus together with the green parahippocampal gyrus in the temporal lobe, and together they circle the corpus callosum, seen here in white, and this makes up the girdle or the limbus that surrounds the brainstem. But let's put this back together for a moment. We can add the brainstem, put the hippocampus back in, and add the thalamus and brainstem. And now you can see the structures that we're going to be talking about today. This animation shows the purple hippocampus as it curves around and follows the ventricular system seen here in turquoise. You'll notice that it's large down in the temporal lobe and becomes narrow as it moves back and up and around. Let's watch it. Now, from the posterior view, you can see the two hippocampal formations in the temporal lobes and see how they come around laterally, but they also curve around and come up dorsally. And the white structure emerging from the top of them represents the fornix, an output bundle of axons coming from the hippocampus. This animation combines both the green cingulate gyrus and parahippocampal gyrus together with the hippocampus, which make up the limbic lobe. And the hippocampus is going to be pulled out, and you're going to see the fornix fibers coming from the hippocampus going down to the septal region and the hypothalamus as they loop over the anterior commissure, which goes across. Let's look at that. Here you can see them coming at you with the septal region in front of the anterior commissure and the brown hypothalamus behind it. And the large fornix, the band of fibers coming out of the purple hippocampus, is bending and looping forward down into the anterior part of the forebrain. Now, let's go to the gross specimens. This hemisection of the brain shows a massive amount of atrophy with a narrowing of the gyri and a deepening of the sulci. But in a way that's nice because it makes it easy for us to demarcate the cingulate gyrus as it comes around. Do you see that? All of this is the cingulate gyrus curving around the corpus callosum. And now as I come down here, I can see how it's continuous with the parahippocampal gyrus, which is here, and the anterior part of this part of the temporal lobe is called the uncus. The uncus is the most medial part of the temporal lobe. So the cingulate gyrus, the parahippocampal gyrus, and then the hippocampus that's rolled up under in here that we can't see is what is technically called the limbic lobe. And now I'm going to add a few more structures because we also use the term limbic system. So let's look at the other components of that system. We're now looking at the temporal lobe on the inferior or ventral surface of the brain. Here's our cerebellum and brainstem, and olfactory bulb and orbital frontal cortex. And here is the uncus, the most medial part of the temporal lobe. And now I'm going to surprise you because as I rotate this over, the hippocampus has already been dissected out on this specimen. So now this is the tip of the temporal lobe. This is the occipital pole still, and this is the left hippocampus coming all the way from here and curving around. And here you can see it here, and you can see this band of fibers. This represents the fornix coming from it and hanging beneath the corpus callosum as it moves forward. Flipping it over now, here's our brainstem, frontal lobe, occipital lobe. That fornix that was hanging underneath the corpus callosum now starts to move medially, and I can see it as it dives down here in front of the interventricular foramen, and it's going to go through the hypothalamus down here to the mammillary body and make a synaptic connection. Part of this is involved in a circuit called Papez or Papes or Papez's loop or circuit. So let's walk through that circuit, which is a cortex-to-cortex circuit that most people believe has implications for learning new material, new explicit memories, not the implicit sort of things that you take when you learn to walk or when you learn to feed yourself. Those are implicit memories. We're talking about explicit memories. So now let's look at Papez's loop. Papez's loop begins with a large area of association cortex projecting onto the cingulate gyrus. The cingulate gyrus has a band of fibers deep in it that comes around and circles down into this parahippocampal gyrus and curves around and terminates in an area called the entorhinal cortex. That entorhinal cortex projects to the hippocampus. But the hippocampus has more structure than you can see here grossly, so let's look at it for a moment in a coronal section. The coronal section of the temporal lobe here, with the lateral fissure, and here we have the hippocampus curled up, the anterior part of it, right next to the ventricle here, the inferior or temporal horn of the ventricle. And right on the surface of this hippocampus, or hippocampal formation, are the axons that are going to form the fornix, that curved around that we saw. It curves around so you can actually see it up here. There's choroid plexus, but this band of white fibers up here is also the fornix. So the fornix coming out of that gets larger and larger as it comes and gathers more axons until it hangs below the corpus callosum. The septum pellucidum has been bridged here, probably because of the increased size of the ventricle here. That's a little bit of pathology. But here's the fornix coming down now. It's going to curve and dive. This part here is going behind the anterior commissure, and this part here is going forward in front of the anterior commissure to the septal nuclei. And down here is the mammillary body, where this part is going to go. And the mammillary body is part of the hypothalamus. So the fornix is going to the mammillary body of the hypothalamus. Now let's look at a coronal section. As the fornix curves down and is going almost vertical here, you can see it on both sides. You can also see the anterior commissure curving across here. So some of these axons are going to go in front of the commissure, and they're going to end up in the septal nuclei, which are right in this region here. And while other axons are coming down to terminate in the mammillary bodies, part of the hypothalamus. On either side, you see the thalamus, the third ventricle. So this is hypothalamus, and this is thalamus. Now, there's a bump here on the thalamus. It's not very obvious, but this little bump here represents a nucleus of the thalamus called the anterior nucleus of the thalamus. And there is a bundle of fibers running from the mammillary body, where the fornix has synapsed, and the mammillothalamic tract travels up to the anterior nucleus of the thalamus. Another relay or synapse there, and axons enter the white matter of the internal capsule to terminate in the cingulate gyrus here. Here's the corpus callosum, so this is the cingulate gyrus above it. And so now we've made a total loop, because from the cingulate gyrus, axons of new neurons go out to other areas of the cortex. So it's cingulate gyrus to temporal lobe to hippocampus, hippocampus through the fornix to the mammillary bodies to the anterior thalamus, and back to the cingulate gyrus. And that is what makes up Papez's or Papes circuit or loop. I have a brain here with severe atrophy, so this is undoubtedly from a patient with dementia. Look how sharp the ridges are of the gyri of the post and precentral gyri here, and also the frontal lobe is severely affected. Not knowing the history, I'm going to say that this patient had Alzheimer's disease, and I'm going to speculate that if we cut a cross-section through here with a knife, we would see a cross-section of the hippocampus, and I'm going to fake that with a specimen from another brain of another patient. This is the brain of the other patient, and this is the normal brain. The first thing you notice about this brain are the enlarged ventricles, not because the person has increased intracranial pressure, but because so much tissue from the cortex and other structures has been lost that the CSF has taken up that space, and so the ventricles looked enlarged. Remember, next to the ventricle was our curled up little hippocampus with all of its parts, which we haven't gone into. And over here on the normal brain, a much smaller temporal or inferior horn of the ventricle, and here you can see the hippocampus in its classical jelly roll curled up position. And the size of the hippocampus on this side compared to the size of the hippocampus on this pathological specimen is almost double. Now, Alzheimer's disease is characterized by tangles and plaques in the cerebral cortex, gray matter, as well as in the hippocampus. And I'm sure if we looked with a microscope, that is what we would find in this patient. So we've been focusing on the hippocampus and its input and output and its relationship to memory. Now we'd like to switch over to another important limbic structure, and that is the amygdala. The amygdala is also in the temporal lobe. It is just anterior to the end of the ventricle, the tip of the temporal horn. It's this large beige, grayish structure right underneath the cortex. This was that entorhinal cortex, and here is our amygdala. Now, most of the amygdala is associated with the limbic system. There's a little bit of it that has to do with olfaction, but we're going to talk about its connections. And one of the most important things associated with the amygdala and its basolateral connections is the emotion of fear. Now, let's look at a coronal section of the amygdala. The amygdala is also associated, you see, with this cortical area having to do with olfaction. And so many times seizures originating in this region begin with a foul, unpleasant odor. And these often smell sort of like rotten eggs, like hydrogen sulfide. And these seizures are, again, indicative of partial complex type of seizure associated with the temporal lobe, sometimes called temporal lobe epilepsy. So I just couldn't resist showing you this beautiful coronal section that shows the amygdala so beautifully, much better than the wet specimens that I had available to me today. And it serves as quite a nice summary. Everything is here just about except the hippocampus. You can see the hypothalamus down here, And also you can see the fornix coming down into the hypothalamus. You can't quite see the mammillary bodies. And you can see the mammillothalamic tract going up to the anterior nucleus. And also we can see the cingulate gyrus here above the corpus callosum. So this is a fun sort of summary, but mainly I wanted to show you how nice and large the amygdala is, how it's right beneath the uncus. And now let's look at an animation. Again, the relationship of the amygdala to the ventricular system is seen here. The bright red amygdala right in front of the end of the ventricle down in the temporal lobe. And you can see the entire structure as it rotates here. Building our mental brain model, now we can see not only the amygdala in red and the ventricles in turquoise, but we can also see the purple hippocampus behind it and the green curving caudate nucleus as it comes around and circles around with the ventricle also. In this peel away of the cerebral cortex, we're going to isolate out the structures we've been studying today and leave only those parts that are current to the limbic system. You can see the amygdala in red, the hippocampus in purple. Notice the fornix curving down and going to both the septal region in yellow and the hypothalamus in brown. These are structures that are intimately involved with the limbic output. We have to end this long session on a bit of amusement, and I thought I would show you the hippocampus in another format. I have to admit that I don't know where I took this image from, but I want to thank that person. What we have on the right is the real dried seahorse from the ocean, and its scientific name, its generic name, is hippocampus. And some ancient anatomists thought that if you dissected out, as you see on the left, the hippocampus from one side of the brain, it resembled a seahorse, and thus we have the name hippocampus. But better than associate it with this marine animal, associate the hippocampus with learning and memory and problems with the hippocampus with amnesia, and then you'll be in better shape since you're not going to be marine biologists.